it says I'm live from here, so that's what I'm gonna just take. I'll take those words. Listen, everybody. Last time we were talking about this electromagnetic induction, and today we're going to get to the next level. But I want you to know this. As I'm going to explain, we don't have to do calculations. Listen, Sinuelo and everybody. Physics has 6 units, right? And we are doing chapter 4. Physics has 1. For you to be a physics guru, how do I become a physics guru? You have to be very good at the 6 units. And when you're doing a past paper, you should see this is unit 1, it's finished. Now we are at unit 2, it's finished. Now we are at unit 3, it's finished. Okay, because all the questions are separated. Each unit comes alone. So there's no mixing in physics. So you have to know the chapters separately, and you should be able to answer the questions. Right. So that's important. Now, what I want you to know is we are doing chapter 4, which is electricity and magnetism. Okay? This chapter, electricity and magnetism. Electricity is nice. Electricity is easy. Electricity does not have a lot of theory. Electricity is calculations. But magnetism and electromagnetism is different. It has calculations. So chapter 4 has a lot of calculations when it comes to, it has a lot of calculations in electricity, but not much in the other parts. So chapter 4 is broken into 3. Listen, chapter 4 is broken into 3. Don't just forget these statements. We don't say them because we are mad. There is no madman here. I'm not a madman. Listen, students. Okay? It's broken into 3. Magnetism and electromagnetism. This is how you approach it. This is how you think when you're doing these things. Don't mix it up. Never mix up anything. When you get a new subject, put the whole structure in front of your eyes and start going through the things one by one. You will love your work. If you just get deep, you haven't even planned, you don't even know the structure of the subject you're doing, you're just learning, what are you doing? That's not what I taught you. That's why you end up hating the school. Because you were just doing it. You didn't know how many topics you were doing. You didn't know anything. You were just doing. That's not how education is done. You organize your stuff. Be organized like a Japanese. Listen now. Electromagnetism is what we are looking at. Listen to these words. It's going to be a bunch of theory. There won't be any calculation. The only calculation we'll do it at the last part when we talk about a transformer. So when we talk about a generator, I want you to open your ears and say, what theory should I know for this thing? When we talk about a motor, I want you to open your ears and say, what theory should I know about this one? Then when you know the theory, you're fine. Don't worry about anything else. There shall be no calculation. There is no calculation on a generator. None at your level. None. And there is no calculation you do for a motor at your level. Okay? You meet it at university level. Even in A level, there is no calculation for generator. No calculation for motor as well. But there's one calculation which is done at A level, which you don't do here, which is for lengths. I'm about to teach you lengths and why length was important in physics. But for IGCSE, we just know why it's important, but we don't actually do the formula. So you don't have to know length is law, the formula. When you get to A level, you will need to know it. It's simple anyway. Listen now. So we have, sir, what are you saying? Electromagnetism. You should know how electricity makes magnetism and how magnetism makes electricity. So when electricity makes magnetism, we'll be trying to make something move. Let me now say this. Okay? You have electricity, but you want to bring water from underground into your house. You need water. And you stay in a very nice place. You're not deep down there where people have to go to the river to fetch water. We want to do high level stuff now. Okay? So we want to just go underground, take the water that is underground and bring it onto the tap. That is called a borehole. in your yard without you having to go anywhere. So this is the challenge that we have. So now people sit down and they start to think, what can we do? We already have electricity. Now we want to try and use that electricity to get water from underground. Hey, they sit down. Then some guy manages to sit down long enough, okay? Get away from noise, sit down and think in a nice environment. He wakes up, he takes care of his body, you bath, you refresh yourself, you drink water, you sit down in a clean environment, you start working out, your mind is working, everything is nice. Then he thought of something called a pump. Now, what is the secret for you to make a pump? This man has to understand this topic. We have another problem, students. I want to go and see my parents who stay in a different country from me. So now I want to go and say, hi Dad, how are you doing? How? Two, testing. Can you hear me? Sorry, it's a problem that was happening. Oh, hi, Anita, welcome back. How are you? So we have problem number 2. Listen to this. Then we'll continue with our work. So you want to travel, you want to go for holidays, you want to go to a different place, you don't want to be in the same place, or you want to go to school, but school is not very close to your house. You don't want to walk. You are not deep down in those in deep areas where we don't have cars and everything. You want to be able to walk, okay? You want to be able to quickly travel to go to school and then go to work and produce, and work and be productive. So now we have a problem because we want to be able to move from one area to another very fast. Somebody had to sit down and try to design something called a car. But for you to do this, you have to understand electromagnetism. Because, okay, fine, you have fuel. And fine, we're going to burn the fuel, produce movement. But now, we want to be able to have electricity generated from whatever, the burning of the fuels, or electricity from the batteries, or wherever you're getting it. All this electricity coming, we wanted to be able to go to what we call the exo in an engine. Okay, in an engine, what we call the exo, which is underground the car, and rotate the wheels. So a pump, a generator, a motor. Yeah? Motor which is in a pump, by the way. A pump is a motor. We want to have all these game-changing developments. A generator in a power station. We want to be able to make electricity. We are going to have big magnets and everything. We want electricity to light up the lights. Everything we are doing right now is because of electricity. If it switches off, there is no lesson. Electromagnetism is a game changer. These are things you have to master right now. Maybe you are going to develop something in the future. A big Hello? Can you hear me, guys? Hello? Can you hear me? It's like today the microphone doesn't want to be touched. I keep touching it. I'll use the second one if it has a problem again. So now, everybody, you have to master this theory and don't be a boring student. Don't be a boring student. Don't forget things we master. We move on. Put them somewhere. Respect knowledge. Electromagnetism is all about magnets to electricity. But there's one thing that people try to ignore, and because they ignore it, they always get stuck. People ignore movement. If you want to have magnets give you electricity, something must move. So magnets will not give you electricity in the air. Okay, you want magnets to give electricity, so you need to put a wire, a conductor close to the magnet where you will get the electricity. Okay, so put a wire close. But now, yes, you have the magnet, my friend. Okay, yes, you have the magnet here. Yes, you have the wire. This is a wire or a conductor. Yes, you have the magnet. This is a magnet. Okay, this is a magnet, but there's no electricity yet. Okay, there is no electricity yet. Yes, you have the wire. Yes, you have the magnet. Move it. Move something. Once you move, you will get electricity. Done. So now we are going to the next step. What we all agreed on last time, okay, was that, okay, what we all agreed on was that when you move, if you move a magnet near a conductor, if you move a magnet near a conductor, then what will happen? You will get an EMF induced in the wire. Okay, I want to write it properly now as one sentence. Okay, if you move a magnet near a conductor, you are going to get an EMF in the wire. In other words, you are going to get electricity in the wire. I explained what EMF was. I said one side will become positive, the other side will become negative. Then electricity will start to flow. So for a current to flow, a current is electrons. Your current flows from positive to negative. When a current is flowing, for a current to flow, you need to have one side which is positive, then the other side which is negative. Then current will flow. Because remember, you are trying to force electrons to go to a negative side. They don't want. So you have to force them by putting an EMF. Then those electrons, which are the current, which will be your current, will flow. So this is what we call this is the flow of current. So when you're writing, you should say, okay, when you move a magnet close to a wire, too close to a conductor, or when you move a conductor which is in a magnetic field, which means close to a magnet, you will induce an EMF in the wire, and the EMF will produce a current. These are some words that we write, right? This is where we were last time. Now we're going to move on to the next part here, but that is your electromagnetic induction. Okay, right, everybody? So what did we say last time? Last time we said when you have a changing magnetic field, that cuts through a conductor. In other words, you are moving a magnet on top of the wire, or you're moving the wire on top of the magnet. Then an EMF is in. Remember, I said last time, this is not fiction. EMF is a word. It's not madness. An EMF means one side is positive, one side is negative. It means potential difference. An EMF is induced in the wire. Are we together? Right. Today we are going to learn how do you increase the EMF. Okay? How do we increase the EMF being induced, the voltage, so that we get more electricity? We want to get more electricity in this wire. So yes, we are moving the magnet, and it's moving on top of the wire. then we're going to have electricity in the wire. How do we increase the amount of electricity? That's where we talk about Lenz's law. And physics actually, A-level physics actually then gives you a formula for you to know how to increase. Okay, so let's go. How to increase the induced EMF. I said induced EMF just means one side is positive, one side is negative. Once you have that, you have electricity, because current will flow from positive to negative. So when you induce an EMF, in other words, you have generated electricity, my friend. So how do we increase the induced EMF, the electricity? How? If you increase any of the following: 1, speed of movement. Speed of movement, okay, of wire or magnet. Okay? The speed at which the field lines are cutting the wire. Remember, they are field lines, right? You have a magnet, right? And a magnet, we said it has field lines, a bar magnet, that come from north and go to south. Okay? You should put arrows whenever you draw a field. We said it last time, like this. So we already have field lines that are coming from north going to south. They are coming out of north and they are getting into south. We already have field lines. So if we move this magnet on top of a wire, we have our wire cutting the field lines. The conductor, we call it a conductor. You have your conductor cutting the field. When we say it is cutting the field, it means that the field that is inside the conductor is changing, because these magnetic field lines are moving. So they go up. They go up. As they are going up, let's say your movement is like this. There's a drag. Give me a second. Let's say you're going up like this. The moment as you are swiping up, you're moving your magnet on top of the wire. One side will become positive, the other one will become negative. Okay? Current will flow. If you now change the direction of movement, you now bring the magnet back down, then the polarity will change. In other words, the negative becomes positive, the positive becomes negative, and electricity will flow in the opposite direction. Electricity will flow in the opposite direction, but it will still flow because you are cutting the field lines with your wire. So how do I increase the EMF? How do I increase the EMF? Increase the speed of movement, my friend. Increase the speed at which the field lines cut the wire. Okay, so speed at which, that's why we don't care whether you move the wire or the magnet. We don't care. The field lines should just cut the wire. So increase the speed at which field lines cut the wire. Once you do that, you are going to get electricity, more electricity. More electricity, yes! We have more electricity now. What is the second way, Mr. Clarify, of us increasing this? Increase the number of turns in the conductor or wire. So instead of just having one thin wire like this, what if we have a wire which does this? Okay, this type of wire is called a coil. And please, I don't want to see weird things. Okay, I don't want to see weird, senseless things. You do not increase the coil. The coil is one. You increase the turns of the coil. Turn, 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 turn. Make it turn more. Then when you bring your magnet north, south, or south, north, and it moves through, whom? If your magnet moves inside this coil, I'm telling you, there's going to be some serious electricity right there. One will be positive and one other end will be negative. And there'll be much more electricity than what you were doing when it was just going over one thin wire. You had north and south, one thin wire, and you were moving your thin wire over this. You were moving it backward and forward and whatever. Nah, come on now. This is just a thin wire. This is just one wire. Make it a coil and see, Mr. Man. We know here was positive, the other one was negative. Okay, fair and fine. There was electricity, but it was little. Increase the number of turns in the coil and see. The more the turns, the stronger the EMF is induced. We already have electricity because we are moving a magnet relative to a wire. In other words, we have a wire and a magnet and we are moving them. One is moving, the other one is moving. So of course we have electricity because we have respected the laws of electromagnetic induction. But now we want to be greedy. We want more. So if you want more, move faster. That's why you see effective pumps and whatever, they can move. They have magnets that are really seriously moving. In a generator, powerful generators, they have, every generator has a big magnet inside it. And let me tell you what they do. So you have a big magnet again. Around the magnet, they start tying the wire, the coil. Then they start to move them like this. They are moving the magnet and the coils. Let me try to see if I can have a diagram to show you. And coil. Look at this. Can you see this? Look at this. We know the game they are playing here. Look at those wires, those serious coils. And they are going to be rotated that with respect to that magnet. Where does a generator get power to rotate those coils? Where does a generator get power to rotate the coils? Where does it get power to rotate? It gets power from the diesel. Isn't you have to pour diesel in a generator or whatever? You have to pour diesel, so it gets power to rotate the coils. Even here, it gets power to rotate. This is the simpler diagram. These are the simpler ones. But if there is no movement, there is no induction. We are not babies anymore. We are not babies. Bring us a magnet, bring us a wire, and move. If you don't move, there will be no electricity in those wires. You brought them for nothing. For design. Really? Come on now. We need electricity. So move the wires, man. Or move the magnet. Move one of them. We don't care what you move. It's just that the wires are easier to move. So you're going to move them. Then these wires will start to have electricity inside them. And we can give it to the people. And the people will be so happy. You as a scientist what you did. You know what you did because you understand electromagnetic induction. Let's go. Move on. You increase the number of turns and you increase the strength of the magnet. Put a bigger magnet. Okay? You increase the magnet strength. then you are going to have more induced EMF. Hmm? You increase that. Are we together? Now, this is so this guy, when you hear people now saying lens, what? What lens was now doing was people are saying, hey, increase the speed of movement, increase the number of turns in the wire, increase the strength of the magnet. People don't just believe when you tell them. So you have to prove what you're saying. So Lenz is the one who actually then showed, he proved to people how to get the EMF. He was calculating how much EMF was induced. He was calculating how much EMF was induced. But okay, but this what I want you to know is that one thing which you must also know is an important thing is that when you talk about Lenz's law as well, okay, this is Lenz. Okay. So what I was telling you was Faraday. You don't have to know Faraday. I'm just remembering. The other thing which people should also know is that, let's say you push a magnet into the coil, right? You take a magnet, you push it into the coil. You should expect the coil to fight back, if I can say it like that. So if I'm going to take a magnet and I push it into the coil, if this magnet is promoting, let me say, it's just a simple concept, okay? If it's just a simple, look at this. If I take a magnet and it's north-south, okay? When you push it into the coil is going to fight back that movement. Okay? It's going to fight back the push which you are doing because it knows you are trying to use it. The coil will know you are trying to, so that the coil will get electricity because you are moving. So this coil is going to have electricity. Now, what you must know is that this electricity will automatically generate a magnet which is going to be opposite to this. So this magnet is going to be south this side and north the other side, opposite to the magnet you are moving in it. So when a coil gets electricity, the electricity it should get should make it be a magnet which is opposite to the magnet that made it. So magnet produced current in the coil. The current in the coil should produce a magnet which is opposite to the magnet that produced it. Simple. Magnet, you produce me as a current. I will make a magnet also which is going to be opposite you so that I fight you back. And this was actually something which is important because when people were doing some experiments, they were getting stuck. And once this person explained this to them, then they understood what was going on. So just write this for now, okay? You'll see where this works later on. Just write for me to say Lenz's law instead of Faraday's law. Okay, Faraday you do it at A level, which is how to calculate the size of EMF. For Lenz, write for me to say nature fights back. So we are already now starting the second area, because what people in this class are beginning to see is that electricity produces its own magnet. Really? Yes. And we're going to study how to see magnet that is produced by electricity. What does it look like? So here, what you must know is that the electricity made here will have a magnet which is opposite to the magnet that was being used. This magnet was being pushed and it was being used to create electricity. That electricity will not be a friend of this magnet. It will make its own field which is opposite this magnet and say, hey, what are you doing moving inside of me? So that's what happens. So nature fights back. Now I'm now writing. Less explaining now. When a magnet is pushed into a coil, the coil creates its own magnetic field. Everybody in class understands this, okay? You're not boring students. You don't forget what we learned. The coil will also have a magnet. But that's not Lenz. Lenz now says the magnet is opposite to the magnet which was making it. So the coil should oppose what's going on here. So I want you to write the magnetic field created by the coil tries to stop the movement or the motion or movement from the magnet producing it. Okay? So if a south, basically what I'm saying is, if a south is approaching the coil will also become a south to fight, to repel this magnet you are pushing in. Are we together? Right. Now, let's do the last part before we do AC generators. How do you know direction of induced current? Isn't we said there's going to be induced EMF? Let me ask you students, okay? Which rule is this that we are doing? What did we start with so far? All the things we have been doing about electromagnetic induction. What did we start with? Are we starting with electricity or we are starting with a magnet? What do we have in the first place? What is the first thing that we have here? Do we have electricity already? In all the situations where we were having a coil and a magnet and whatever, did we have electricity? Speak, students, come on now. Did we have electricity? We didn't. But in the end, we ended up having it, right? So what are we doing? What are we doing here, student? We are generating electricity, right? So this is how a generator works. So we are studying the generator. Can you hear me? What is happening in a generator is electromagnetic induction. There are wires, coils, and there is a magnet, and they will be moved, and you have electricity in the coils. So you have generated electricity. That's what's happening. Now, let's just say what we want to study now is how do we know the direction that current will move when we see the direction we move the wire or the magnet? How do we then know the direction that your current will go? Okay, because we want to know the true direction of current. If you do it the wrong way, of course everybody knows, if you connect things the wrong way, you can bend things. So we want to know what is the true direction of current, okay, for the questions that you may get. And I'll show you how they give you questions, okay, so you know. How do you guess the direction of current? I said, if you are doing generator rule, listen, don't let me down. This is not a motor here. A motor is what you find in a pump. A pump which pumps water. It starts with electricity. It's connected to electricity. So electricity is already there. Make no mistake there. Electricity is already there. So in a pump is the motor rule, because we are having electricity first. That one, you use the left hand. You use your left hand. Whatever we are going to do there, the types of questions we'll do, we'll be working with the left hand. Here we are doing the other thing. Why do we do left for motors? Because motor cars move at the left hand side of the road in Botswana and in Southern Africa. Okay? And in England. Motor cars move at the left hand side of the road in these countries. So you use the left for motor. Motoroo for motor cars, you use the left because they move on the left. Then for the generator, you just use your right hand. All you gotta do, I'm a bad artist, honestly. Let me see if I can do this. Yeah, that's good. This is true. This is the right hand. This is the thumb, finger number 1, finger number 2, finger number 3. Okay? Finger 1, 2, and 3. And remember, I told you last time, FBI. So, FBI. Hands up. The FBI is here. 1, 2, and 3. F is for force, which will be the direction of movement, because the direction the force is applied will be the direction of the movement, or thrust. Thrust is a force. Then this B is going to be, you study it at A level, is the symbol for magnetic field. So B is the magnetic field. Then I is the symbol for current. Everybody knows that. You know the symbol for current is I. Don't pretend now. Don't pretend. This is going to tell you direction of induced EMF. They'll say the right hand rule, right hand, whatever. This is just the right hand rule. It tells you you only should, we don't want to see this rule if you are not generating electricity. When you are generating electricity, that's when you're going to use it. You can spin the hand upside down depending on the situations. So they will tell you you're going to have a situation, and what they'll be wanting to know is which direction will we. So we are moving this thing up and down, and the field is like this. Which direction will the current flow? We're going to bring out our right hand and predict. That's easy, right? Students? This is easy. And once you do this, now you have to know one last thing about generators. This generator rule, which we have been doing, and it will be the end. You now go to the next thing. Okay? All you have to know is AC generator. This is the last thing you have to know for this section. Let me give you some few notes, and then I show you the diagram, then you stop. Okay? It will take me 2 minutes. Just write with me this. I want to give you some important things. Okay? Okay. Write this. We use electromagnetic induction to generate electricity continuously. We use electromagnetic induction to generate electricity continuously. Okay? Now, what I want you to remember, don't let me down. Induction is inducing an EMF. You just should have a changing magnetic field next to a wire, once you have a changing magnetic field in the wire, then you will induce an EMF in the wire. So we are inducing an EMF. So electromagnetic induction. To induce, induction, the word is here. You are inducing an EMF. In other words, you're creating electricity, sir. Come on now. This is about a generator. So once you are able to do this continuously, you will now have what we call a generator. So generators convert movement, because they have a magnet, they have a wire, they move these things, then they will have electricity. So they convert mechanical energy. Mechanical energy means things are moving. This is physical stuff. To electrical energy. Where is the mechanical energy coming from? From the fuel. That's why you need fuel. There's no abracadabra. Tell them, man, to say, hey, I need fuel so that I can move these things. I want to move the magnets or move the wires, but they must be next to each other, and I should move one, then I will get electricity, because I come from mechanical energy. Movement to electrical, not just any movement. Movement of a magnet close to a wire, or a wire next to a magnet. Then you're going to induce an EMF. Okay? Right. Let's do an example. Example of this. Let's say you turn a turbine at a power station. Okay. Turbine spins. Turbine is a fan. A turbine is a big fan. I once explained to you people to say what they are doing at all countries that all of you are have thermal power stations. In Botswana, it's Morupule, right? In Zim, it's Wange. You have thermal power stations. They put coal. Coal is just like firewood. Okay, it's very good like firewood. It's like firewood. It can burn. They light it up. Coal will light up a big fire, but that's not electricity. Wait. You say, okay, what happens next? They put water in big containers. They boil the water, really, really boiling it. So the coal is a source of fire. To boil, it will light up a fire, boil the water, and the water is in big tubes. You have a fire now, and the fire is coming from coal. Okay? There's coal inside here. Coal. And here is your fire. And it's burning. Now you're going to have steam start to go out. And there's a big fan called a turbine. A turbine is just a fan which has like a metal which is connected to something which are the coils here. Okay, you have your coils. Let's just say it's connected to the coils. Like when it rotates, how should I put the coils? Here are the coils. Coil, 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 coil. All of them are connected here. So this big fan, turbine is just a fan. What it does, it's gonna be pushed by steam. Steam is coming at high pressure. It's coming at high pressure. Starts to turn the tip. Vroom, 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 vroom. This is your generator here. The coils are inside the generator. So the coils start to go. They start to turn. They are turning inside the generator, and there's a magnet, big magnet at the center here. Let's just say this is the magnet, and these are the coils that are being made to rotate. Guess what you're going to have? Electricity, which will now go to your houses. electricity which will now go to all our houses. Electricity which will now go to all our houses. Where did it come from? The power station. So this, the spinning of a turbine. Turbine spins. Okay, this is the example. So you say turbine spins, and what will happen? This is mechanical energy. Okay, mechanical energy. Coil will rotate. This is mechanical energy, and this rotation will now produce electricity. So you now say this is step 2, this is step 1. Step 3 is electricity is produced. So this coal is your fuel. It is the fuel to power what? To power movement. This is what happens. Now, for you, you have to know the AC generator. You should know the AC generator. Let me tell you the parts. You should know the parts. Then I'll show you the diagram. Parts of an AC generator. So, what is an AC generator? Okay, so there's another subject, another part of electricity, which we are not going to look at today, which I won't talk about today too much. But I just want you to know that we need electricity, which is called AC. If it's not AC, then we cannot transmit it nicely. When electricity gets into your phone, it will no longer be AC. You'll be now having it be converted to DC. But then, all the way until it gets there, it has to come as AC. AC means electricity which goes in zigzags. It goes, comes back, goes, comes back, goes, comes back, goes. This actually helps. You know Tesla, Elon Musk took that name and used it for cars. There was a person who was called Tesla, and that's not Elon Musk. That person was there a long time ago, and he's the one who did this to show that don't make electricity just go. Make it go in zigzags, then it is going to have more power. And it turned out to be true. It's weird but true. So an AC generator is what we need because all our houses need AC. Right. Okay? That's why solar panels need an inverter to convert the DC to AC. Right. So that your house has the proper electricity, not the fake one. Your house needs AC. So the parts of an AC generator, you have a magnet, you have the rotating coil. Everybody knows these things should be there for induction. Isn't that what we said it uses? It uses electromagnetic induction. Then there are two things that people confuse: slip rings and brushes. These are different. Slip rings are connected to the wires. They carry electricity. They carry AC, which is the electricity. Okay. Brushes are there for electrical contact. I'll show you. Okay, you have the rotating coil. The coil is the one which is moving. It's easier to move the magnet than the. It's easier to move the coil than the magnet. Magnet will be just creating its magnetic field, a region around it, where if you cut that region, there will be electricity in the wire. The rotating coil, it cuts field lines. So why we love a generator is it can convert fuels to electricity through going from mechanical energy to electrical energy. So now we have electricity. Yes. Okay. I'll show you the diagram. Okay. I'll show you the diagram. Just remember. Okay. Let's write here. I gave you the 4 parts. Just write the last part, then I'm done here. I'll show you the diagram. Okay. Of this, so that you know the diagram is very easy. You need to know the diagram because you need to be able to label it. But you must the biggest thing is you must know why AC is produced. Why do we have these generators that we are talking about producing AC? So I'll show you a DC generator versus an AC generator. Okay, can you just write here to say okay, maybe not. Let me not do it. I'm going to do it in our next lesson when I bring the diagram. So I'll bring the diagram of AC and DC because a lot of you will be confused by what we mean by half turn. Okay, what we mean half turn. But let me just say, as coil rotates, as the coil rotates, okay, current flows in one direction in the first half of coil rotation. Then in another, in the second half, current then flows in another direction, or you can say then in the opposite direction. Okay, then current flows in the opposite direction in the second half of coil rotation. So now, okay, this produces an alternating current. In other words, current which goes forward, backward, forward, backward, forward, backward. That's an zoo, 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 as it moves. This is an AC current, and this is what you get. Now, we'll see in our next lesson the diagrams and how we can improve a generator's output to make it overperform. We want the generator to overperform, but these things you should be able to explain how an AC generator works and why we get AC. The reason we get AC is because of the rotation of the coil. The direction in which your coil is going to determine also, because let me say this. Your coil is like this. Now, in the first half of rotation, you have a magnet, of course, and another magnet here, of course. Because the wire should rotate. This is just a simplified version of the diagram. Can I ask you, if the coil is rotating like this, right? In the first half of rotation, this side here is going up, right? And this side is going down. Is it not? Until your coil gets to the point where it's upright, like this. Until your coil gets to this point. Now, guess what? In the second half, this side which was going up is now going down. And this side here is the one which is now going up. So the sides have changed. The one which was going up is going down. The one which was going down is going up. Now you cannot ignore direction of movement. That's why we did the right hand rule. You can't ignore direction of movement. If this wire was going up and electricity was going this way when it was going up, when it starts going down, electricity will go the opposite direction. Man, it will be induced in the opposite direction. That is why we get AC. First half, the left side of your coil is going up. So current is going, maybe flowing out this side and whatever. Second half, that side is now going down. Then now it will change in the wire. And you start to get an AC. Squeeze, 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 squeeze. When it's rotating, so it will go, because it's rotating. When it's rotating, the current goes there. It goes forward, backward, forward, backward, forward. Because now it's going up, then it goes down. One side goes up, then it goes down. Then so when it's doing like that, that's an AC. That creates your AC. Remember just to say it. It's so easy. The direction of movement is going to affect the direction in which EMF is induced. Why are you doing that? The right hand rule. It is used to determine the direction of induced EMF. And when the movement is different, then the induced EMF will also be in a different direction. You are not letting me down. Don't be a boring student. Don't just forget. You hear about a generator, you know about a generator, then you actually forget. That's boring. I always have to tell you the same generator. I want to tell you more nice things. So come on now, keep this. Keep this stuff. Keep it safe. Don't lose it. Then we do the next hard thing. We need to do the motor. Then we need to do the transformer. We want to know, why does it have a soft iron core? What does the word soft mean? Why do they use the word soft in a transformer? Why do they have this? We'll talk about it. And where does it come into all this? Why is it in this chapter? Where do we have the magnet going to electricity and electricity to magnet in a transformer? Why is it in this section? We'll talk about it. All these machines work differently. For people to discover them, they sat down and thought out. This guy really did very well. Now we understand what he was thinking. And this is easy. We just need to make a coil rotate. Whilst we have a magnet, then we're going to have electricity in that coil. So we need to be able to just design our things nicely. Then we can get a generator and we can generate electricity. Anyone with a question? Students, is there anyone with a question on this simple stuff? Good.